on behalf of the International Society for Neglected Tropical Diseases, a very warm welcome to all to this first ISNTD conference on climate and health. Over the next 2 days and in the run-up to COP27, we're very much looking forward to exploring with our speakers and you, the participants, all the linkages between climate change and diseases, with a particular focus, of course, on infectious and tropical diseases. My name is Marianne Compere. I'm director at ISNTD, and once again, a really warm welcome. Thank you so much for joining us today. So this is a very exciting and important event we have ahead of us. We will hear more about the evidence linking climate and health on the one hand, with presentations of work covering a variety of diseases and perspectives from a range of countries and regions. We'll also seek to understand the ways in which the two sectors can better work together. And perhaps you yourself are attending because you may be wondering how to include climate change and its impact into your own health. So we'll also hear more about methodologies, whether in terms of modeling, programmatic integration, or just basic research. And we do hope that throughout the sessions and these 2 days, one very clear point will stand out, and that is that climate change disproportionately affects the world's most vulnerable, and neglected tropical diseases too disproportionately affect the world's most vulnerable. So although health impacts of climate change are increasingly part of the wider climate discussions, there's still a long way to go in terms of making this a priority. And this is why we feel really strongly that the time is right now, to fully realize the impact that the field of global health can make in terms of the understanding, the response to climate change, and also as a critical partner in terms of resilience, response, and adaptation to climate events. And this is the way that we want to frame this event: climate change as a global health issue, and those working in the fields of infectious diseases and global health as crucial stakeholders in the complex climate change discussions. So where do we start? Perhaps that in itself is quite a good place to start. Where to start when thinking about climate change and its impact on diseases. And so it's my greatest pleasure to open the day and to welcome our first panel of speakers to help us with just that, and talk to us a bit more in detail about the linkages and the evidence of these linkages between climate and health. And so I'm sure everyone will join me in welcoming very warmly our first speakers for the day. We've got wonderful opening remarks and a fantastic way to frame this day. So without any further delay, I'm going to hand over the floor to Diarmid to tell us all about linkages between climate change and diseases, but also very importantly, the role that the neglected tropical disease community has to play in this very important integration of sectors.
Hello, I'm Diarmid Campbell-Lendrum. I'm the head of the Climate Change and Health Programme at WHO headquarters in Geneva, and apologies for not being able to join live for this important meeting and important discussion. It is of particular interest to me as somebody who, before I started to work on climate change, I have a background in vector-borne disease. I did my PhD on African trypanosomiasis, and then postdoc work on leishmaniasis and Chagas disease, and a little bit of dengue work as well. So that the diseases that the conference covers and the interaction with climate change, I think is not only interesting, it's also critically important. A part of the transition that I made as I moved from being an academic researcher looking at some of these issues to work at WHO on climate change was firstly to look at the burden of disease that was caused by climate change around the world. And as I started to look at the work, the models that we had to look at the health impacts of climate change, some of the earliest work that was done in this field about 20 years ago was exactly on the interaction of climate change and some of the neglected tropical diseases, particularly vector-borne disease. And some of that earlier work people listening to this will be aware, did relatively simple modeling of the effect of temperature and precipitation changes that were starting already to be observed of climate change on the transmission of some of those particularly vector-borne diseases. And I would say that in those early stages of the discussion, it was relatively contentious and not always very constructive. That discussion tended to take an either or position, either the suggestion that the effects of climate change were the main determinant of the distributions or the incidence of those diseases, or the contrary position that other things were the determinants of those diseases, poverty, poor living conditions, and failure to put into place control measures. And that either or debate, I think, rather hampered the field. It was rather less than constructive. I would say that I think we're in a better position now as we look at the interactions between climate change and neglected tropical diseases. It seems very clear now, as the evidence is mounted, of the reality of climate change, of the fact that it's clear that humans are the main cause of the climate change, which is now developing into a full-blown climate crisis. Not only is that very clear, but it's very hard to argue that changing the world's climatic conditions, changing the world's temperature, changing its precipitation patterns, and so on, that could occur without having an effect on diseases such as vector-borne diseases or diseases transmitted through water, or diseases transmitted through soil or other environmental stages. It will be hard to argue that you can change the world's climate without having some effect on those diseases. At the same time, the evidence has continued to mount, and we have better and better quantification, better understanding of the effect of those other determinants of those diseases as well. The effects of poverty, the effects of weaknesses in health systems, and the effect of neglect that is basically the defining characteristic of NTDs. The fact that those populations which need the most support in terms of health services are the ones that get the least support. So those two realities, I think, have a large evidence base behind them. It's also very clear that they interact as well, that those populations which are most susceptible to the health effects of climate change are those which have those weaknesses in terms of poverty, in terms of the other environmental and social determinants of health, and of neglect by health services and by the rest of the world. So that interaction means that those populations are the ones which have most to be concerned about with climate change, and should therefore receive the most support. And that's why I think this discussion, this conference is so important. There's a practical agenda there about what we do as part of combating the climate crisis to protect those that are most vulnerable, including from the effects on neglected tropical diseases. And it seems quite obvious that there are several things that we need to do. Research and better evidence is clearly important. And again, as part of the neglect of neglected tropical diseases, we know that not enough investment goes into research on these diseases. And an important consideration here is the kind of research that we do on NTDs. Another of the things that's become clearer over the past 20 or so years that we've worked on climate change and health at WHO is that research on many health impacts, including the health impacts of climate change, is rather unbalanced. We tend to get rather a lot of research on better quantification and better understanding of the problem, and not enough research on the interventions that we need to put into place to protect people from those problems. And that's a feature of climate change and health research that we're trying to address. So that, I would suggest, is one of the things that should be discussed within this conference. And I think from looking at the program that you will hear what look to be excellent presentations about some of the work that's going in being put into place now about, for example, the use of climate and weather information to improve risk mapping or to improve early warning systems for some of the most important neglected tropical disease. So research, and particularly research on interventions, is a critical need for, I think, for us as a global health community. Another need is actually to put into place those interventions. And again, we're getting better and better understanding not only of what interventions we should select, but also how we should deploy them as well. And it's also been a trend, I believe, with our colleagues who are working on the neglected tropical disease side of the problem, as opposed to the climate change and health problem, that we should be looking at these things less holistically. And the new strategic plan and roadmap for NTDs that WHO has developed in consultation with the wider health community places a much greater emphasis on working holistically, working on systems-based approaches, working on determinants of health, and not only vertical individual programs on individual diseases. That, again, interacts very well with the approach that we're taking on climate change and environmental determinants of health. We simply don't have the resources to be able to fix these problems only at the end of the line when we're talking about individual diseases. We do have to go upstream in order to work on systems-based approaches that can help to support work on these diseases as part of prevention, promotion, and protection of public health as a whole. And that's one of the most important points that I wanted to leave you with. Some of the causes of climate change and the causes of neglected tropical diseases are common causes. If you think about the causes of climate change, it's largely due to unsustainability and inequity. It isn't the case that we don't have enough money or resources to fix climate change. In fact, fixing climate change pays for itself. The problem is that the control over those decisions is not in the hands of those people who are most affected by those decisions. It's in the hands of a smaller number of people who have more to gain from continuing business as usual, and therefore the perpetuation of the climate crisis. And I think some of those same considerations play out in the causes of neglected tropical diseases. Part of that neglect, or a large part of that neglect, is inequity and unfairness, that we don't, as a global community, devote the resources that we should be devoting to combating these diseases, which tend to affect the poorest populations of the world. So there is an interaction there. In fact, we would have much less to worry about in terms of health impacts of climate change if all populations had strong public health services, if we had better water and sanitation services, if we had the coverage of the interventions that we already know work for some of these neglected tropical diseases. So there is a common cause there in inequity and failing to protect the most vulnerable. And I think that's also one of the final points that I wanted to leave you with, is that as we look at these common causes, we also do need to look upstream as well, that we do have a crisis of sustainability and we do have a crisis of equity. There are more than enough resources in the world to deal with all of these problems that we're discussing. So I hope that in the rest of the discussions that you have throughout the course of this conference, that you talk about some of the excellent research that's being done to characterize the problem and to characterize the best interventions, but also to think holistically about how we implement that as a systems-based approach, but also to recognize that we have to work together, we have to support each other, whether our day job is more on neglected tropical diseases or on climate change and health, or on climate change, or on poverty and inequity, because we're not going to solve any of these problems in isolation. It is effectively all part of sustainable development. So I wish you very well for your conference. I will pay a great deal of attention to what comes out of this, and I hope to engage further in these discussions and to work with you in the future. So thank you very much.
Very big thank you to Diarmid for this amazing framework and lens through which to really think about the integration of climate and tropical diseases, how How lucky, how brilliant, in fact, that the head of climate and health at WHO has such a strong background in neglected tropical diseases. So that's been a real bonus. And while Diarmid was giving us much food for thought on how to think about this conference and what, how to really position ourselves within that, lots of colleagues have joined from around the world. So I'll just say a quick hello to, we have so many. Helen Mayfield from Australia. Hello. Keleja Velo from Albania. Nice to see you here. Celestine Madongo from DRC Congo. Nice to meet you. Neela Mikbal up in Liverpool here in the UK. Also Aisha Sarath Chandra from Sri Lanka. Tishali Yadita from Ethiopia. Hello, everybody. I can't list and name everyone, but it's really nice to see such a wide range of participants from all around the world for these really important discussions. And after the presentations, there will be an opportunity to ask questions or perhaps even share your own experience, your own work. So please do go ahead, put your comments and your questions in the chat, and we'll be monitoring that and bringing them into the discussion in about half an hour or so. But now I'd love to hand over to our next speaker. So Dr. Tristan McKenzie, who's at the moment with the University of Gothenburg, but will be presenting work that was also undertaken at the University of Hawaii at Mānoa. It's not every day that we have the absolute pleasure of welcoming a marine biologist, but I guess that's where we have to go to find a scientific colleague who can really talk about the whole scope and breadth of diseases that are impacted by climate change. Tristan, I'll hand over the floor to you, and we really look forward to hearing all about your research showing that over half of known human pathogenic diseases can be aggravated by climate change. So thank you for joining us.
So hi, thank you again for the invitation today, Marianne, and thank you to everyone attending. I'm going to be presenting some work that I did with colleagues at the University of Hawaii at Mānoa, as well as the University of Wisconsin. And as Marianne mentioned, my background is actually not in health per se. It's actually, I'm a marine chemist, and I actually do a lot with water quality. This has been a really interesting project to be a part of. So today I'm going to be talking about the results of our recent paper that was published in Nature Climate Change, entitled "Over Half of Known Human Pathogenic Diseases Can Be Aggravated by Climate Change." And I'm honored to present this on behalf of my co-authors. Numerous studies have documented the impacts of climate change that it is having on disease on local and regional scales, but no previous work has conducted such a comprehensive review to fully understand the threat that humanity is facing from climate-aggravated disease. And this is what we attempted to do in our study. First, I'm going to give a bit of a background on climate change and how it's currently impacting our lives today. I assume that many in this group are well acquainted with these impacts, but it's always good to cover the basics. So just some basic information on the greenhouse effect. This is shown by the figure on the top left of the slide. Earth is warmed by the sun, and then much of that solar radiation is then absorbed by Earth's surface. This is then radiated from Earth's surface as infrared energy, where some is then absorbed by the greenhouse gas molecules that are in the atmosphere. And what's important about this is that greenhouse gases mediate the balance between solar radiation coming from the sun and outgoing infrared radiation from reflection off surfaces. Additionally, once these greenhouse gases are in the atmosphere, their impacts are long-lasting. And so, for instance, carbon dioxide will remain in the atmosphere for 300 to 1,000 years and will likely lead to lasting changes, some of which we're already experiencing now. And the plots on the right side of the slide show carbon dioxide in parts per million and that are in the atmosphere. This top plot shows the concentrations since 1960, when carbon dioxide levels really started to accelerate following World War II. The bottom plot shows carbon dioxide concentrations over time from about 40,000 years ago to present. And this graph is a few years old, but the orange arrow shows where we are now. And you can see it's off the chart. We're actually off of the scale now. Humans have never before lived in a world consistently beyond 400 parts per million carbon dioxide, and that's where we are today. So the Intercontinental Panel on Climate Change, or IPCC, outlines 5 different emission scenarios for the next 100 years. And in particular, I want to point your attention to the RCP 2.6 and 4.5 pathways where human-induced warming by 2100 remains under 2 and 2.7 degrees respectively. For a long time, this 2-degree benchmark was seen as a feasible goal, but also one with significant consequences. Now, even several years later, the best estimate for where we're headed is 2.7 degrees of warming, assuming that the Paris Agreement holds. Both of these scenarios require substantial mitigation of greenhouse gas emissions. And it is also worth noting that many climate scientists believe that 4 to 5 degrees of warming by 2100 is likely. And the consequences of even 2 degrees of warming are severe. When most people think of climate change, they think of the weather, but climate change has widespread influence on pretty much every aspect of life as we know it. And so here, once again, I've pulled a figure from the IPCC report that shows the degree to which climate change is already contributing to physical, biological, and human systems on Earth. This map represents the current situation, but one should expect that this story will be significantly worse should we continue to use fossil fuels. And these impacts are already being observed to be dramatically worse in less wealthier nations and in equatorial and polar regions. So here's a figure from Mora et al. In 2014 showing projected impact of climatic hazards under the RCP 8.5 scenario. And briefly, red indicates an increase in a hazard and blue indicates a decrease. And again, I just want to point out that the equatorial and polar regions are especially impacted. So in our work, we considered 10 different climatic hazards. As I mentioned before, greenhouse gases mediate the balance between solar radiation coming in from the sun and outgoing infrared radiation from reflection off of surfaces. And so this figure shows a simplified view of how these various climatic hazards that we looked at in the paper can influence one another. So excess greenhouse gases in the atmosphere cause warming, and this warming allows the air to hold more water, allowing for more evaporation to happen at a faster rate. This process then leads to excess drought in dry places, and then heat waves can occur when the heat transfer for water evaporation no longer occurs. This also leads to increased opportunity for wildfires to occur. This accelerated water evaporation for warming can also lead to increased precipitation, which if it occurs over a short period of time, can lead to flooding. And then warming enhanced evaporation of ocean water enhances the strength of storms and can also lead to storm surges impacting sea level and thus also flooding. Ocean biogeochemical and physical changes such as warming, ocean acidification, changes in currents, these all fall under ocean climate change. And then finally, we included land cover in the paper because of its impact on greenhouse gas emissions and its demonstrated effect with disease transmission. So in our research, we carried out 3 complementary literature searches following the PRISMA guidelines for reviews. For our search, we specifically looked at empirical case examples where a specific climatic hazard influenced a specific disease in a specific place and time. So that means that our results should be considered conservative. We used Google Scholar to find our papers, and for the first search, we searched the word disease along with each of the 10 climatic hazards. In the second search, we looked for each of the 10 climatic hazards and the diseases listed in the Gideon and American CDC databases. This includes 375 diseases in all. For the final search, we wanted to confirm that we didn't miss any diseases, and so that we searched each disease and pathogen name synonyms. We conducted a comprehensive review of the available literature, but it should be worth noting that there may be a publication bias towards examples with negative consequences or for diseases that are less rare. And so, for instance, the neglected tropical diseases may be less represented in the literature. We took extra measures in our search, such as documenting all examples of climatic hazards leading to not only aggravating disease, but also to cases where there was no effect or that a disease was diminished to make sure that we accurately represented the available literature. And it is also worth noting that our study demonstrates the linkage between climate change and disease, but we did not specifically evaluate the impact that climatic hazards have on frequency, severity, or prevalence of specific diseases. All right, so what did we find? Here I show a simplified version of our online interactive database, which you can access following the link on the slide. It's right here on the bottom. I'll pop that link up again. And this figure shows the numerous pathways that these greenhouse gas-driven climatic hazards via a variety of transmission types can aggravate human disease. Line thickness is proportional to the number of diseases impacted, and the numbers indicate the number of diseases. So, and each column is in order of decreasing number of impacted diseases. So just reading off of the top, we see that warming was associated with aggravating the greatest number of diseases. That is 160 different diseases. Vector-borne transmission was associated was the most common transmission pathway, responsible for aggravating 103 diseases, and that viral diseases were the most aggravated, 76 diseases. Breaking this down a bit further, we found that 58%, that is 218 out of 375 diseases impacting humans, are aggravated by climate change today, as is represented in the literature. Of the documented cases of diseases influenced by climate change, we found that 78% were exclusively aggravated by climate change, with only 3% exclusively diminished. And in addition, we found over 1,000 pathways for climatic driven disease transmission. Again, vector-borne transmission aggravated the greatest number of diseases, and warming, precipitation, and flooding led to the increase in the most diseases. And moreover, we were able to put all of the case examples we found, they all fell under 4 different mechanisms for climate pathogen interaction. These were climate-related hazards bringing pathogens closer to people. So for example, warming and precipitation changes were led to increased habitat suitability for vectors at higher latitudes, elevations, as well as temporally, such as vectors being able to survive over winter months. This has also been associated with the range expansion of vectors such as mosquitoes, ticks, fleas, snails, birds, mammals, pretty much you name it, and has led to outbreaks of mosquito-borne diseases such as dengue, chikungunya, and Lyme disease, for example. The second mechanism we found was climatic hazards bringing people closer to pathogens, where people can undergo a forced displacement due to a hazard occurring. So for instance, storms and floods have led to increased cases of waterborne diseases such as cholera and leptospirosis. Our third mechanism that we found was climatic hazards enhancing pathogens. And this includes, for example, improved environmental stability for vectors. For instance, storms, heavy rainfall, and flooding have led to increases in stagnant water, and thus have been associated with leading to increased cases of mosquito-borne diseases. And then the fourth mechanism we found was that climatic hazards can reduce human capacity to cope with pathogens. For instance, through forced exposure to pathogens such as unsafe conditions, damaged infrastructure, reduced access to medical care, and also as well as the impacts that stress can have on the human immune system from living through a hazard. And so, for instance, we found that drought led to reduced sanitation and was implicated in increases in a large number of diseases, for instance, dysentery and E. coli. So I just want to flash up the web tool again. This is a fully interactive database where you can find all of our case examples online. All of the papers that we read are linked in PDF form, and it is also searchable. So if you're interested in a specific location, for instance, if you just go up to the entries link, you can search the database for whatever you're seeking. And yeah, so just leave with a couple take-home messages. The first is we found that 58% of diseases impacting humans are aggravated by climate change, with over 1,000 pathways for climate hazard pathogen transmission. Secondly, that atmospheric warming, rainfall, and flooding were associated with enhancing the most diseases. And finally, the reduction of greenhouse gases is absolutely necessary given the magnitude of diseases impacted. Disease mitigation strategies really benefit wealthier nations, and so really are not a solution, or not the solution, not the primary solution to this problem. Thank you.
Thank you so much, Tristan. That was, I think, exactly what was needed to open the day. It was really useful, actually, to have that recap on climate change right at the start of your presentation. Thank you so much. We're going to hone in a little bit more now, specifically on neglected tropical diseases. Dr. Rachel Tidman is going to present to us another literature review, but of all the work that's been done linking climate change specifically to neglected tropical diseases. And Rachel's speaking to us from the OIE. So I'll hand over to her now.
Good afternoon, morning or evening, depending where you're joining from today. Thank you so much for the opportunity to present our updates on climate change and the impact that this may have on neglected tropical diseases. Please do feel free to contact me following today's event, and I'd be more than happy to discuss the presentation or paper further if you're interested. So I'm sure you're all very familiar with this group of diseases, but this is the list of diseases classed as neglected tropical diseases by WHO. And you can see here that we have a huge variety of pathogens, many of which don't seem to have a lot in common. What they do all have in common is that they disproportionately impact vulnerable populations in low resource settings in tropical and subtropical areas. Now, these same communities are often suffering the greatest consequences of global change, particularly climate change. We're also seeing displacement of populations, so partially due to armed conflict and political upheaval, but also because of food and water insecurity, which is aggravated by climate change events such as severe droughts. And this displacement, combined with limited resources and health infrastructure, will exacerbate the disease burdens in these communities. And in addition to this, any change in epidemiology and distribution of these diseases may also then put additional populations at risk and undermine any current disease control programs. The WHO NTD roadmap, released earlier this year, sets out targets for the prevention, control, elimination, and eradication of these diseases by 2030. We know that interventions to prevent and control NTDs are one of the best buy-ins or investments in global public health. We also know that NTDs are important traces for identifying disparities in progress towards universal health coverage and equitable access to high-quality health services. However, climate change, along with all these other factors, may change the transmission period and geographical range of these diseases, potentially resulting in encroachment on regions and populations that have been previously unaffected. And in order for this roadmap to have the desired impact, we need to be looking at ways to improve surveillance and monitoring to make sure that we're actually identifying areas of NTD incursion and emergence, and making sure that these are then included in future public health interventions. So we set out to conduct a systematic review of the available literature on climate change and NTDs, looking to identify correlations with climatic factors that influence trends in disease transmission and distribution. We also wanted to identify geographic areas and populations that might be at risk of disease incursion or re-emergence under future climate change scenarios that may not necessarily be included in current disease control and surveillance programs. And the aim of this is that we could potentially help predict disease distribution and improve targeted public health interventions. What we confirmed by this exercise is that there are complex interactions influencing these diseases and these trends. So these diseases vary considerably in their epidemiology and transmission. Some require vectors or intermediate hosts. Many have a range of reservoir species, all of which influence the epidemiology quite dramatically. And of course, climate change isn't happening in a vacuum. It exists in this complex matrix of other factors which further complicate matters. So globalization, changing land use, movement of humans and animals, urbanization and population growth, all of these contribute to changing disease epidemiology. Now, it was unfortunately impossible to isolate specific predictions. They all conflicted based on geographical area, what disease we were looking at, and what vectors and hosts were involved. But we did find some general trends, particularly for vector-borne diseases. And in particular, looking at temperature and rainfall, We found that temperature influenced the lifespan, reproduction rate, and feeding rate of vectors, while rainfall impacted the availability of suitable breeding habitats. We saw anticipated changes in transmission periods and geographical range of many of these diseases, with an overall trend of shifting into higher altitudes and latitudes. We also found that there were possibilities of vector and reservoir species shifting as transmission changed, and the studies we reviewed highlighted the complexity of some of these transmission cycles. For example, Chagas disease, which has a huge number of competent vectors, all of which had varying habitats, a range of different reservoir hosts as well, and varying thermotolerant ranges. And as I mentioned, these are all the other factors as well that, that feed into these trends. And often the predictions or modelling conducted in the studies that we reviewed didn't include these confounding issues. So it was often very unreliable as to what these trends were doing. For example, we've seen the introduction of competent dengue and chikungunya vectors into Europe following importation of goods. We've seen outbreaks of schistosomiasis in Corsica, France, following movement of infected people from endemic areas. We've also seen local transmission of leishmaniasis in Central Europe, potentially driven by movement of domestic dogs. And things like deforestation and changing land use and housing quality will influence human exposure to vectors for Chagas disease. And these factors often exacerbate the changing trends of disease that we're seeing with climate change. So perhaps they then allow the introduction of vectors or pathogens, which because of the changing climatic factors, are then able to become established and set up local transmission cycles. So dengue and chikungunya really highlights some of the changes that we saw. There was a lot of literature around these diseases, primarily focusing on the changing distribution of the vector. It's very difficult to pin down really precise predictions, as I mentioned in the previous slide, but we did see a few trends happening. So for example, increased temperature could increase the development rate and vector biting frequency and potentially accelerate viral amplification. But past a thermotolerant threshold, increased temperature could then also decrease the survival of vectors. Similarly, although rainfall could increase the number of suitable breeding sites, so could decreased rainfall, which then resulted in water storage behaviours by people. Conversely, increased rainfall could then also result in flooding and the destruction of breeding sites. So it's very difficult to get a clear idea of what the trends were with specific climatic factors. But we did see that potential for a changing geographical distribution, and we have already in fact seen local transmission in previously non-endemic areas, often following the introduction of a suitable vector. We may also see changed seasonal patterns. So warming winter temperatures may mean that instead of having seasonal spikes, we might start seeing disease throughout the year. There was much less available literature on other NTDs, such as rabies and snakebite. There was a possible change in the distribution of rabies wildlife reservoirs. But these papers were focused primarily in North America, which doesn't reflect areas where the true burden of rabies is felt, so in Africa and Asia. Snakebite envenomations may also see a range of trends, so increasing temperatures may result in increased foraging behaviour and contact with humans, but it may also drive some species to extinction. Both increased and decreased rainfall, again, were discussed as potential for driving increased contact, making it difficult to predict some of the changes we might see. And of course, this is heavily dependent on geographical areas and the snake species involved. So in terms of consequences, what does this then all mean? So the obvious one is that we might see the incursion and re-emergence into new and naive human populations, resulting in increased morbidity and mortality from these diseases. But it could also mean detrimental impact on control programs. Changes in reproduction rate of intermediate snail hosts, for example, may result in these species rebounding much faster following snail control efforts. Lymphatic filariasis is considered eradicable, but what will the change in geographical distribution do to control programs for this? And we focus very much on human health, but we also need to consider the impact this has on animal populations. Diseases such as trypanosomiasis can have an enormous impact on livestock productivity. And if this was to spread into densely populated agricultural areas, we'd not only see an increase in human cases, but an increase in livestock cases. And this would contribute to the spillover in humans, but also result in significant economic losses and exacerbate issues of food insecurity and malnutrition in communities that are very heavily dependent on livestock and agriculture. So what are some of the things that we can do to manage this and mitigate it? Well, to start with, we need far more evidence. We can see some trends emerging in the literature on climate change and NTDs, but without taking into account all these other factors, we'll be struggling to make reliable or useful predictions. We specifically need evidence and robust surveillance and monitoring in high-risk and vulnerable areas. Many of the studies that we reviewed focused on changing disease risk in developed regions, but the predicted impacts in developing tropical and subtropical areas were much less consistent, despite the heaviest burden of these diseases being in these areas. And developed regions are much more likely to have the surveillance systems, the healthcare systems, appropriate sanitation and hygiene, and all these things will likely mitigate the risk associated with vector and disease incursion. In contrast to this, vulnerable populations are more likely to lack the surveillance and infrastructure to prevent and respond to disease emergence due to global changes. So we really need to be identifying these at-risk populations and then building the programs and systems to respond accordingly. And finally, we need to be ensuring that we implement One Health approaches. Many of these diseases are zoonotic in nature and have a variety of reservoir and intermediate hosts and a variety of environmental drivers. So we can't be expecting to address these appropriately without including these sectors in our planning and implementation efforts. Thank you all very much for your time, and do feel free, as I said, to get in touch if you've got any questions. Thank you very much.
A really big thank you to Dr. Rachel Tidman there for this presentation and this overview, not only untangling a little bit the very complex impact of climate change on these 20-odd varied and different diseases, but also the very complex world of climate change, and which immediately links to migration, change of land use, urbanization, and so forth. So a great framework to start putting a little bit in order in these very complicated dynamics. So I'd like to thank our first three speakers who've really set the scene here on a global scale for what we need to be thinking about and what we know in terms of the linkages between climate and health. And so at this point, it's my pleasure to welcome our fourth speaker, Dr. Mark Booth from the University of Newcastle, who's going to take us a little bit away from this global view down to the local view. What do the linkages between climate and health mean when you're talking about neglected tropical diseases right down to the local level? So, Mark, for this really important and interesting point of view and perspective, I hand over to you now, and thank you for joining us.
Thanks, Marianne, for the invitation to join you today and to discuss the issue of why I think scale matters when we're controlling or planning to control NTDs now and into the future. And I'm distinguishing here between a changing climate and climate change. We could argue, there is no argument really, that climate change is occurring and will occur many decades into the future. But what about contemporary thoughts? We're living, I think we can term this as a changing climate. We see it every day. We see reports of extreme weather events. We understand now more as a population, as a global population, that climate change is affecting populations now, but will continue to do so, even with massive interventions. It's inevitable that things will change. one of the big questions is how things will change, and climate change is just that. It's a change, and it could go both ways depending on the context. And I'm going to explain to you a little bit some of my research that I've done collaboratively over the years to try and think about what happens at the local level, but also regional level, and how we can try and address those two things simultaneously, because there are some conflicts. Now, scale. What does it mean when we're talking about trying to consider interventions and prevention and control? Well, scale happens at every point in a society. It doesn't matter whether you're a stakeholder, a policymaker, a researcher, a citizen. You live at a particular place, and that place is a very local area, but you live within a community that is larger. You live within a region, and it could be an administrative, a political region. You could be bounded by natural or purely human administrative boundaries. You live within a country that is governed by a government. You live within a continent that has natural and man-made features. But going further down than that, even within communities, within villages, within households, within people, there are cells and molecules. There are parasites that have parasites that have parasites. The scale is very different. It works at every level. And we have to think really carefully about what scale is appropriate for control of NTDs in a changing climate and with the prospect of climate change. Now, my work has often focused on what I would call small area variations, and I'm going to give you a couple of examples of that, and then I'm going to finish with a contrast to that, which is working at a more regional level, and then think about some of the issues and how we can address those. Now, this is a collaborative study that took place some years ago in Kenya, and it took place in a couple of villages. Now, these villages are susceptible to exposure in terms of schistosomiasis mansoni, which is a parasitic fluke that infects hundreds of millions of people across the tropics and the subtropics. And the point of this particular research project was to test a combination of mollusciciding and chemotherapy to reduce transmission in these two areas. And the two villages were given different treatments. So one village was given a molluscicide over 4 years. This was administered into the local stream, the Thangi River. So there's two rivers here, the Thangi River and the Kambu River. And each of these villages was either given molluscicide or no molluscicide into the streams to kill off the snails to test whether that reduced transmission. So this is a local study. Now, during that particular research study, there was a freak storm, which was later attributed to an El Nino extreme weather event. And why this is becoming interesting in the context of climate change is it shows what can happen at a very local scale when there are extreme weather events. So what I'm showing here is a graph from the paper that was published in 2013. And on the x-axis, there are months. And this is in the early 90s. So we're going from January. Each of these letters corresponds to a different month. And the number of snails that were recovered in the village that received the intervention of the mollusciciding. Now, what's important here is to notice that there is natural variation in the population of the snail over year because environmental conditions change throughout the year. There are periods of drought and there are periods of rainfall, and the snails respond because they have to respond to the differences in water availability, the temperature, and so forth. So it's a natural phenomenon to see variation. But what happened was that at one point there was a freak storm, this El Nino attributed event, that washed away all the snails. Effectively, there was rapid extreme flooding in this river and the snails disappeared. But what's important to note here is that they came back. And just before the mollusciciding started, there was actually a small resurgence. So there was a period of time when there were no snails, and then there was a period of time where there were some snails. And these snails are responsible for the transmission of schistosomiasis. They carry the parasite in them and release them into the water. So in the absence of snails, there's no transmission. But this extreme event did in fact clear out the snails for a while, but then they came back. And this tells us something about the adaptability of these organisms to extreme weather events. Although climate change is thought of and is due to anthropogenic influences in the large part, the climate has always changed, and these parasites and their vectors and their intermediate hosts have been through many eons and cycles of changing climate. And as long as the environment is still present, there are opportunities for those snails and other vectors to return, even if there has been a temporary effect by an extreme weather event. So that's one point I want to make. Now, over time, there was a success story in the sense that the combination of chemotherapy and molluscociding was successful in the short term. But you can see here that this didn't last very long, because over years, if you look at 2002, 3, 4, and 5, after the end of the molluscociding, after the El Nino event, the snails came back and transmission continued. And this is why it's important to keep going back to the same places sometimes and think about what might have happened in the short term, even after there has been an extreme event. You can't just rest there and say, oh, well, they've gone, they're never going to come back. They may well do come back. They may well come back. And therefore, it's important to continue with surveillance in these areas that are susceptible. And surveillance is one of the key take-home points, I think, about trying to mitigate uncertainty. No one could have predicted the freak storm with any certainty, and nobody could have predicted with any certainty when the snails would come back, and therefore represent a hazard to the people living there. So the conclusions from that study was that this El Nino attributed event in 1997 disrupted the snail populations for approximately 2 years, but there was a reduction in intensity of infection, and that was largely attributable to a combination of the extreme event, continued molluscociding, and also chemotherapy. So in combination, they all did have an impact, but it was only felt in the short term. The second example I want to discuss this morning is now a research project I collaborated on in Uganda on the shores of Lake Albert. And I'm showing a map of an area where there is a village spread out along the coastline. And you will see that this map consists of a number of symbols. And there are triangles that are both open and have no color, and then there are black triangles. And they represent the households of people from different ethno-linguistic groups. And they occupy different parts of this village. You will also see, so the green is the land and the blue is the water of the lake. You will also see that there are squares and circles, and these squares and circles represent the two different intermediate hosts of Schistosomiasis mansoni in this area, Bionfilaria sudanica and Bionfilaria stanleyi. And the size of the circles and the size of the squares indicate the relative abundance. So these data were collected through surveys, and the snails were counted in situ, so where they were. And you can see that the snail populations vary in terms of their abundance at different points along the graph, along the map, sorry. And you can see that one of the snails, Bionfilaria stanleyi, was found in a wider distribution than the other snail, Bionfilaria sudanica, which tended to be more inland in the marshy areas. Now, each of these, we know through other previous work, have a different sort of carrying capacity for the parasite. And what we found through this research study was that they were differentially affected by changes in the lake. So the lake was changing in terms of its environmental parameters. And I'm going to show you now some of the results of the research that looked at how the snails were affected by those environmental changes. So what happened during a period of between 2000 and 2002 was that the lake level increased significantly at the shoreline. So there was a lot more water going into Lake Albert, which would be a result of, for example, extra water coming down the Nile, but could also be due to increased levels of rainfall, for example, and other factors that raise the level. So the important thing here is not how it occurred, but the fact that it did occur. There was a raise in the level of the lake and more water, therefore, present in the system. And that's seen very clearly on the graph on the left-hand side. Now, rainfall during this period of time went up and down, up and down, up and down. So the influx of water was not due to additional rainfall. In this particular case, it was due to probably more water coming down the Nile, which drains into Lake Albert. Now, what happened to the two snails was quite interesting to observe, because the lake level was increasing, but the Bioinflaria stangii that prefers deep water actually crashed during that period. Now, typically snail populations go up and down depending on local conditions and the temperature and other factors associated with the water at different times of the year, but there was a definite trend downwards, and by the end of 2002 the population had crashed. Bioinflaria sedanica, on the other hand, seemed to increase, going through greater amplitude of change over time, but also by November 2002 had crashed. So at the end of that period, the snails were very rare, they weren't really found. Now, what this suggests is that each of these snails have preferences for certain environmental conditions, but when those conditions become too extreme, in this case the lake level becomes too high, neither of them can survive very well. So this could be an example of where climate change affects the environment so much that the vectors, the intermediate hosts, cannot survive. And that means that if we move into more extreme climate scenarios, there may well be some areas that become less hazardous in terms of parasitic infections, because those areas can no longer be inhabited by the vectors, the mosquitoes, or in this case, the intermediate host snails, and that means they will be wiped out. Now, tie that into the previous research study that shows that even in extreme events, even if they temporarily wipe out a parasite or a vector or intermediate host population, may only be that situation may only exist for a short period of time, maybe a couple of few years. So what we need to be careful of is assuming that when something happens to finish off a parasite in a particular area, that is the end of the story. We really do need to keep going back and re-establishing contact with those areas and ensuring that there is continuity in terms of surveillance. Now, the issue of scale matters because of two things. One, the future can be thought of in either days, weeks, months, or years. Now, typically, climate change projections have been made over decades, and this is a classic image that I've showed many times, and it's relevant in any discussion about climate change because it shows the uncertainty that we're dealing with at any scale beyond just the immediate day-to-day. So climate change projections typically are found in the literature to cover many decades, and those decades may be up to 2100. But as we move further into the future and think about, in this case, emission scenarios, so this is projected emission scenarios based on whether governments do or do not act to limit emissions. But what you can see is there's lots of lines, and these lines tend to go in one direction, they're going up or they're coming down. And there are these representative scenarios, the RCPs that were mentioned before in a previous talk, and they are just representative of all these different scenarios. But we really don't know what the future holds. It's impossible to predict with any confidence into the future. As you move closer to now, then of course the variation is less. So we can predict what might happen next week, next year, based on what we know about global cycles, but it's very hard to predict what might happen into the future. So when we're thinking about the scale of control, and we combine that with, say, the WHO roadmap on NTD control that goes to, say, 2030 or 2040, we have to be aware that even by 2030 or 2040, we're in the realms of the unknown. We really don't know what's going to happen by 2030 or 2040 in terms of the environmental parameters that shape the transmission potential and the natural history of these infections. We have to be aware of that whenever we're talking about discussing the end game for NTDs, and this is typically what the World Health Organization does, that the end game might be changed. It's not really fixed yet. We really don't know what's going to happen because of this issue of the time element, but also the spatial element, and also whether or not the parasites are able to adapt to those environmental changes. Now, I said that I'd moved from looking at very local stuff to more regional stuff in terms of research interests. And this is a collaborative study that was funded by the EU a number of years ago. And I want to show it because it highlights the difference in the approach that is taken when doing comparing local surveillance and monitoring and measurement with climate change projections. There's a couple of things really to note here. One is that this is a fairly high resolution map of the potential changes in the habitat suitability for the snails that I mentioned before that transmit schistosomiasis mansoni. But it covers a wider area. We're not talking here about a village, we're talking about a region of several countries, including Rwanda, Burundi, Zambia, Kenya, Uganda, and Tanzania, all pointed out here on the map. There's another thing to bear in mind, and that is that it's necessary to look at these different scenarios of a low warming, moderate warming, or high warming. So each of those different scenarios, we've had to think about all of them simultaneously, and also think about scale in terms of whether it's near decades or far decades. So the example given here is 20 years or 50 years. And each of these maps is a little bit different. You can see the colors change, and that's indicative of the fact that over these time periods and under these different scenarios, the future will look different. And we have to be aware that it could be any of these. Now, that's very different to looking at a local scale. Yeah, this is a projection over decades. It's over a large region. And although this is quite a detailed map, it still doesn't tell us what's going to happen in one village in 10 years' time. It simply tells us that a region might be more susceptible to schistosoma transmission because the habitat becomes more or less suitable in a period of time. Now, this slide sort of summarizes some of the issues, I think, and I'll just walk you through it a little bit. Now, what we're facing is an increased global temperature. It's very clear that temperatures are going to rise. How much they will rise, of course, we don't know, but they're inevitably, I think, going to rise. And that's going to have a number of effects. In some areas, there's going to be decreased regional precipitation, including drought and more episodes of extreme droughts that last for longer. But in other areas, there's going to be increased precipitation. There will be floods and extreme events, one of which I've illustrated to you earlier. Now, those changes are going to then affect global systems and local systems simultaneously. And there's going to be a number of intermediaries on each plate, on each side of this. So an increased global temperature could actually improve the habitat suitability of areas that are currently too cold, for example, to support the parasites and their intermediate hosts and the vectors. And so that might increase transmission. On the other hand, increased global temperature might decrease the frequency of contact between humans, vectors, and zoonotic hosts because they have to they move away from that area. They're forced to migrate because the environment is no longer suitable. So actually, the contact between people and the transmission organisms, the organisms that transmit the parasites to them, might actually decrease, and that would decrease transmission. Decreased precipitation might force regional level migration as well, and that might actually move people into more suitable habitats, or the habitats might decrease in size and therefore again have a deleterious impact on the ecosystem and the parasites and the vectors and intermediate hosts. And then floods, it's a similar issue, that there may well be pressures on the parasites and intermediate hosts that leads to adaptation. On the other hand, there may be asynchrony because in the short term, at least, the environment is not suitable because of extreme conditions. So I think what we're looking at here, and other presenters in this conference have alluded to this fact as well, that it is complicated. It is a complex system, and there is no one answer. There is no way in which one organization, one individual, however well-intentioned, one researcher, one stakeholder, one company, no one can do this on their own. It has to be a collective effort. Now, what are the ways in which we can think about being collective? I think there are a number of things we can do. We can develop better decision support tools. You may have heard of this thing called if this, then that. And that is the bedrock of a lot of decision making where a certain situation arises and you do something about it based on that situation. Improved surveillance is part of that, and also capacity building, because we can't just assume, and there was the first presentation by Dr. Lendrum pointed this out, that the resources simply aren't there really to make massive gains in terms of enlightening people to the problem, but also putting in resources for successful interventions. I think what we need to do in the future is be able to have a much better view of the global, regional and local distribution of these infections through surveillance at various locations. You can see I've just constructed this map here. You'll notice there are lots of little squares, and they are units that you can imagine exist. You can overlay this onto a map. It's a grid that you can overlay, and you conduct surveillance at each of these points in the grid. Now you then monitor what might be happening, and there are what we might call tipping points that happen at specific locations, and that might be that global warming leads to increased rainfall at a specific location. It may be a dam construction that leads to slow-moving water that supports the snails that transmit Schistosomiasis mansoni, and so on. And land use change, livelihood changes, these all have an impact, and this comes down to these. Sorry, this involves a decision support tool because you can make a decision based on the observation. That can then lead to more intensive work around understanding how that change affects the hazard and the vulnerability of local populations. And then location-specific actions can be taken. Now, this is a framework, and of course, it's very easy in a way to put a framework. The problem is, how do we translate this framework into reality? Well, that involves bringing in more people. It involves increasing awareness. It involves championing. WHO, I think, has a unique role in this because of its ability to reach out, and through its roadmap, I think it should make a lot more effort to understand some of the challenges. At the moment, it only mentions climate change half a dozen times, and so it's really incumbent, I think, on WHO and OIE as well to ensure that their documents, their recommendations, their people have that link. It's not a case of being interested on, as Dr. Lendrum said, climate change or NTDs. There has to be an interest in these organizations that crosses over and has NTDs and climate change thought of simultaneously. Thank you.
Well, a huge thank you to you, Mark. You're a parasitologist by training and you work in neglected tropical diseases, but every time that there's a presentation by yourself, we are thrown into the deep end of multidisciplinary thinking. So that's been really brilliant. Thank you so much. And so at this point, I'd like to invite you and Dr. Tristan McKenzie back on screen to take a few questions and perhaps share a bit more of your experience as researchers. We've got Tristan here. I suppose you'll be representing kind of the climate side. Mark, you'll be representing the diseases side. Obviously, you're both very multidisciplinary in your approaches. But maybe for our audience who may not have been so comfortable working across both sectors, one of the first questions I perhaps would like to ask you on a personal level is, coming from your main discipline, how have you found work crossing that bridge to sort of the other disciplines? What were some of the challenges? What did you find easy? And perhaps what would be some of your main advice to someone who really wants to bring in those dimensions into their own work, whether it be on the climate side or on the diseases and health side? Perhaps Tristan, you'd like to go first?
Yeah, sure. Thanks for the question. I think it takes a curiosity and then also finding the right collaborators to really dive into an adjacent field. It's, I think, a very worthwhile venture, but it is also quite challenging because you're leaving a world where you have that baseline understanding into something that you realistically maybe took a class or two in at a point, right? So it's a lot of effort, but I would say it's very worthwhile, and I think increasingly important. Like, we really need a lot more of these interdisciplinary ventures in science, in social sciences as well. We need to do a lot more working with social sciences as scientists or physical scientists. So yeah, I would say collaborate. That's my biggest advice.
So just jump in at the deep end. Thank you for that. What about yourself, Mark?
Yeah, I would echo that. I think collaboration is key because no one has all the skills all the time and is available to employ all the skills all the time. What we can learn from each other. I mean, I certainly spent some time learning about climate change. It was not a subject I started my career with, and I had to learn by reading and doing. And being involved in the study that I described at the end, this healthy future study I've talked about before, was really my first main introduction to climate change. And I used that opportunity to learn more about it till I became more fluent about it. But I wouldn't call myself a climatologist. I can't. I'm somebody who tries to work at the interface of climate change, environmental change more widely, and using climate change as an example of how environmental change affects parasitic infections. What I bring is a biologist's perspective combined with ecology. So that's where I train. And I've then thought, well, if we need to think about the future, climate change has to come into that discussion. So it's incumbent on me, as someone who tries to be multidisciplinary, to at least connect the dots a little bit. So I would encourage anybody who feels that they have a vested interest in their future to at least try. You know, it's not about being utterly successful at everything, but if you try and raise your own capacity of understanding about a subject, you will eventually. You know, you read, you look at the subject, you try and understand, you reach out, you let people reach out to you. And this is why I think collaboration is key. It's got to be, I show another slide in another presentation that just shows how many different stakeholders can get onto this. You know, it's
quite simply to get to grasp with some of the jargon. I know in NTDs we use a lot of abbreviations. They might not be second nature to colleagues, but also the way that the climate sector thinks and the words they use may not be very evident to someone who's not really read a lot of the research or really gone into it. So perhaps a very simple first step is just to find a lingua franca between the two sectors, not just in terms of vocabularies, but also maybe the indicators or what we're trying to work towards.
Yeah, I think that the jargon is very difficult. Sometimes collaborate or try to collaborate with people in business, and business terminology is very hard to get your head around sometimes, and some of the acronyms especially. Yeah, I think it's very important for anybody who has the knowledge to be able to talk in a way that other people will understand. You know, it's very difficult sometimes. Scientists are as guilty of this as anybody, of using their own knowledge to make themselves look important and sound important because they have the knowledge. And I think it's incumbent on us to ensure that our messages are widely understood. I spend some time lecturing students of different stages, and I always have to be careful about how I frame the discussion and how much detail I go into. And these are students at postgraduate and undergraduate level. But if I make a presentation to a wider group, it's much harder for me to actually frame that way of talking in a way that I know is going to be understood. So every time I use the word representative concentration pathway, I know I'm entering a minefield, and I usually don't even have the time to explain it properly. You know, what does it actually mean? What are emissions? And what does watts per meter squared mean? What is forcing? What is climate forcing? What is downscaling? You know, these are all terminologies that I've learned, but I've had the privilege of having the space and the time as part of my work to learn it. Other people might just shake their head and just go, I don't know, and therefore it's not important because they can't understand it. So I think more effort is required by scientists, but also I keep coming back to WHO here because I think they really have a responsibility to do this. You know, they are the ones who can produce the infographics. They have all the influence in terms of reaching into governments. They have all the stakeholders. I think they can really make a bigger difference than just the scientists alone.
Great points. Tristan, would you like to add to that?
Yeah, I absolutely agree with everything that Mark has said on this. I agree, especially the jargon, and fully or attempting to have a full understanding of what the jargon entails is quite a undertaking. But absolutely worthwhile, and absolutely also the public outreach and reaching various parts of society. Think about how you distill your message in a way that isn't full of jargon is really key for especially starting some of these collaborations with someone from another field.
Brilliant, thank you. So that will be a first action point for all those participating. How do we integrate these if originally they are not interoperable? For example, ecological data on the one hand, and then health and socioeconomic data on the other. So just kind of honing in a bit more on the data. How do we break those silos?
Yeah, absolutely. I think this was actually one of our biggest takeaways from doing this research, is that there are these silos of research and significant data gaps. And significant data gaps, I think, where the data are the most important. How do we break this? I don't know. I would suspect some international movement for monitoring. Implementing this is a completely different question. But I agree. It is, I think, one of our biggest challenges with addressing these problems.
Mark, have you found that too?
Yes. I'm not amused, am I? Yeah, I think this is a very good question, actually, because it is a great challenge to put together very different sectors and different sources and types of data. And I think there are ways to do it. There are methods. They're often iterative and discursive type of methods. One you might have heard called the Delphi method, and that's where you kind of ping the ideas between different stakeholders until you reach a consensus. And that requires some discipline in terms of thinking, but it is open to different types of collaborators who have to, within that method, come to an agreement on how to act, even if they're coming initially from very different directions. The other thing to do, I think, is to actually work out how you can merge the different datas. And I think one way to do that is to ensure that the data are collected at as higher spatial, temporal, and socioeconomic resolution as possible. And what I mean by that is you can aggregate from a very small scale to a very large scale. So you can take village level data and you can an aggregated score that covers, say, lots of villages or households within a village. But if you only take 1 point of information from a village, you've lost all that information from the rest of the village, only that point you've taken it from. So I think it's very important to collect data contemporaneously. So if you're doing a study in a village, try and widen the scope of that investigation as far as possible, so that you collect all the information you can, geotag everything, geolocate everything, so that you have that information always, and then you can attach. Once you geotag something, you can attach almost anything else to it. Yeah, so you can use that latitude and longitude as a way of tagging everything about the socioeconomic status, about the ecological status. It all comes down to tagging and everything. That's a unique identifier.
Eternal question. I think you've touched a bit on that, Mark, just now, but you're both incredible examples of these kind of cross-disciplinary academics and researchers. What are the gaps that are frustrating you the most, and what are your next steps in terms of bridging the two fields together?
I think Diarmid put his finger on this. There's not enough research going on. Operational, basic, translational, it's just not there. And it's notable that most of the papers, so I wrote a paper, a review in 2018, and looked at the citations, and most of the citations of that review are other reviews. But it just seems to be going around in circles at the moment. There's lots of people thinking in a scholarly way about these things, and we've seen examples today. We're all doing the same thing. We're just reviewing. Yeah, all the presentations today about reviews. And so it's clear that we've reached some kind of blockage. There's not enough research going on, so everybody's resorting to reviewing the situation. Yeah, so there has to be, something has to unlock here. There has to be more funding for all these types of research.
I will echo that in the preparation of this conference, although we did manage to fill an entire session later on today with basic research focusing on specific diseases. So please don't miss that. But definitely, I guess it's just perhaps an apprehension, even if you're working with a disease that has an element of seasonality in it, it's just kind of a big jump to then bring in climate issues and data into that, so perhaps people are just shying away from it. But hopefully the next session, which will focus the next 3 sessions actually, whether it be on modeling, whether it be on specific diseases, will inspire the audience on kind of thinking in those ways. Sorry, I just wanted to say, yes, you're right, Mark, it's tricky. Over to you, Tristan.
Yeah, I mean, I absolutely agree. And I think especially collecting a very good temporal data set where you can for sure say, well, here's this climatic event, here is this disease. It is challenging, right? Which is one of the reasons I think increased monitoring in general, better tabulation of outbreaks of diseases, of, I mean, even symptoms, right? Gastroenteritis type symptoms, I think would really help, along with, of course, geotagging, as Mark said, because that is very, very easy to do and very, very informative data. Yeah, I think going forward, especially noting a lot of the neglected tropical diseases, areas that we really aren't monitoring.
We're coming up to the end of the time for this session. I just really wanted to thank everyone who participated. It's been so difficult organizing all this knowledge or the gaps in the knowledge even. And I think our 4 speakers this morning have done that brilliantly. We've also heard really practical recommendations where the gaps are or what needs to be done or how to overcome some of the difficulties in working with whether it be data or the language or just broader collaboration. So it's been very, very useful. Thank you so much. And particularly Tristan and Mark for joining us live for this discussion and Q&A. We have further sessions, so there's 7 in total as part of this conference. And before we leave, just again, another huge thank you to all the speakers today. And I hope that we will be in touch very soon. We can't wait to see what you will be sharing with us in the future very soon, hopefully. Thanks for joining us and all the best.